When we write the permutations in their simplest form, we want to write them as a product of disjoint cycles. It's always better to leave your permutations written that way. So, for example, if you were given the permutation 1, 2, 4, 2, 3, 5, you see that these 2, 3 cycles are not disjoint. I see we have a 2 in this one and a 2 in this one. So I want to multiply these together. Not really multiply function composition, but we'll just use the term multiply. Okay, so function composition you always read this way. And so first, well, I'll put 1 down. And I look and I see what this permutation does to 1 is it leaves it alone. And then I plug 1 in here and I go to 2. So 1 is moved to 2 by the product of these 2 cycles. All right, now I go to 2 on the right again. 2 is sent to 3, and then that's plugged into this one, and 3 is not moved. So 2 is sent to 3 by the product. Go back to 3. 3 goes to 5. Come over here, plug 5 in, and 5 is fixed. So 3 goes to 5. Back to the right, 5 goes to 2. Because it's closed here, it goes back to the beginning. 5 goes to 2, and plugging 2 in here, we see it is moved to 4. And now 4 is fixed, and here 4 is taken to 1, so I close. So now this is the proper way to write that cycle, that permutation. This is a permutation, but it's the product of 2 permutations in Sn. And in simplified form, it is the 5 cycle on the right. Let's see, one other example. Let's take 1, 2 times 1, 3, 2. Again, these are not disjoint. There's a 1 and a 2 and a 1 and a 2 here. So I'll write down my 1. 1 goes to 3, and over here 3 is fixed. Come back to the right, 3 goes to 2, and 2 is sent to 1, so I close. And now let's check everything out. There's no 4s or 5s in here, so nothing happens to them, but let's check 2. 2 goes to 1, 1 goes to 2. So this, in simplified form, is just a 2 cycle, 1, 3. If you see something written like this, 1, 2, times 3, 4, 5, you're done. That is, those 2 cycles are disjoint, and it is, you just leave it like that. Disjoint cycles commute. Others do not if they're not disjoint. So let me show you an example. If you have this 1, 2, 3, 4, 5 that we just wrote up there, if you multiply it out, you'll see it's 3, 4, 5 times 1, 2. It doesn't make any difference. If they're disjoint, you can move them all around. But if you take 1, 2, 3 and multiply it to 2, 5, you get, well, you're not going to get, let's put it that way, 2, 5 times 1, 2, 3. They're not the same. If you multiply this one on the left, you will get 1, 2, 5, 3, and that is not what you get on the right, which is 1, 5, 2, 3. You check that yourself. Here we talk about the order of an element of the group, not the order of Sn, which is n factorial, but the order of a permutation. Sigma is the smallest natural number n, such that sigma repeated n times will give us the identity permutation. So let's call this permutation here sigma 1, 2, 3, 4. And let's see. Well, I'll do it out this time, and then I'll show you an easier way to take powers of these. If we look at sigma squared, that's 1, 2, 3, 4 times 1, 2, 3, 4. And we will get 1. Now watch what happens. 1 goes to 2 and 2 goes to 3. So we get 1, 3. And then 3 goes to 4 and 4 is taken back to 1, so we close. Now we want to see what happens to 2. 2 goes to 3. Ooh. 1, 2, 3. I'm sorry. I had an extra digit in there. 2 goes to 3 and 3 goes to 4. 4 goes to 1 and 1 goes to 2. So we close. There's no 5 in there, so there's nothing moves 5. So that's sigma squared. Now let me show you another way you could do that, because you're just repeating the same cycle, 1, 2, 3, 4. If I square it, notice I just say 1 goes to 2 to 3. I'm just going to skip 1. So I get 1, 3. And then 3 would go to 4, which goes to 1. Closes. Now I take 2 and I skip 1. 2 to 3 to 4 and 4 to 1 to 2. So you can actually just take powers of cycles by skipping the right number. Let's cube it. So sigma cubed will be, I'll do it out the long way once, 1, 2, 3, 4. That's sigma times sigma squared, 1, 3, 2, 4. Now powers of one element always commute in a group, so it wouldn't have mattered if I had put sigma squared times sigma, because powers of sigma will commute. Alright, so let's see. What we get is, we'll put down a 1. 1 goes to 3, which goes to 4. 4 goes to 2, which goes to 3. 3 goes to 1, which goes to 2. And 2 goes to 4, which in turn gets sent back to 1, and we close it. Notice also we could have done it the other way. If I just write down sigma right here, this was sigma, I can cube it by just going up to sigma. Not sigma squared, go back up to sigma and say, well, here's sigma of 1, sigma squared, sigma cubed. So I'm just going to skip over 2. And I get 1, skipping 2 will go to 4, skipping 2 will go to 3, and skipping 2 will go to 2, and skipping 2 sends me back to 1. And you go ahead and calculate sigma to the 4th, and you will get the identity. A 4 cycle goes back to itself after 4 applications of that permutation. Notice if you go up here and raise it to the 4th power, you're going to skip 3. So it'd be 1 goes to, skip 3, 1. 2 goes to, skip 3, 2, etc. All right, now here it says find the order of this permutation. But that is not written in its simplest form. They are not disjoint cycles. So if we want to call this thing something, that's fine. But let's rewrite it in its simplest form as a product of disjoint cycles. So I put 1. 1 goes to 4. 4 is fixed, 4 goes to 5. 5 goes to 2, and 2 is fixed. 2 goes to 3, 3 is fixed. 3 goes to 5, and 5 back to 1. I close. So beta is really just a 5 cycle. And the order of beta, by the way, I didn't show you this, we use the same notation. The order of beta is 5. The order of an n cycle, just one n cycle, or m cycle, is m. In general, the order of an m cycle in Sn is m. So if sigma is a 3 cycle, the order is 3. But remember, always write them in simplest form before you start computing or before you try to find the order of the element. Always put it in as a product of disjoint cycles. Alright, so here we're going to calculate the order of some permutations, and I'd like you to see if you could generalize. Here we have a 2-cycle times a 3-cycle, and they are disjoint. So if I call this, let's say, beta, I want to know the order of beta. Well, if I square it, I'm going to get, just skip over 1. 1 goes to 3 and back to 1. So 1 and 3 are going to be fixed. If you want to write those down, you get this. You don't need to. Now, 2 will be sent to 5 by beta and then 4 by beta again. So 2 goes to 4, and 4, skipping over, will go to 5. And 5 will go to 4 and then to 2. So beta squared is just the 3-cycle 2, 4, 5. Beta cubed. Just go back to beta. You don't even need to look at beta squared and multiply it to that. Just go back to beta and you'll see, if you put down 1, 1 will go to 3, then to 1 and back to 3. So we get our 2-cycle back again. 3 will go to 1, 1 will go to 3, and then back to 1. So now our 2-cycle comes back. And this one, we're cubing it now. So we're going to skip over 2. 2 will go to, skip 5, 4, back to 2. 5 will go to 5, 4 will go to 4. So beta cubed is just this 2-cycle. Beta to the 4th, go back to beta. If you raise a 2-cycle to the 4th power, it's going to disappear again. And this one will just come back. So we have 2, 5, 4. Beta to the 4th is just this 4-cycle. You can multiply them out and check this for yourself. But when we cubed it, it disappeared. So multiplying one more of these, we just get 2, 5, 4 back again. And now beta to the 5th will give us, well, beta to the 5th is going to put our 2-cycle back in there. And beta to the 5th will be, oh, well, you might want to write this out, 254 times 254, but it's the same thing. Beta to the 5th will be 2, 4, 5. And now beta to the 6th will be equal to, well, the 2-cycle disappears again, and 2, 4, 5 times 2, 5, 4 will give us the identity. So the order of beta is equal to 6. I know you guys are going to need a little more time on that. You might want to write it out, but check and see that you can get that one. You might have to write out more. And we'll do more in class. I just don't want to make this video too long. So what the order of it was 6. Notice you had a 2-cycle and a 3-cycle, and the order was 6. Now in the next one, if we call this thing, let's call it gamma. If we square it, we're going to get, well, 1 will skip over 3 and go to 2. 2 will skip over 1 and go to 3. And 3 will go to 1. And this will be 4, 6, 5. Gamma cubed, applying gamma, if you just go back here to this, and 1 skip 2 sends you to 1. 3 skip 2 sends you to 3. In fact, everybody gets sent to itself. So we say that the order of gamma in this case is 3. We had disjoint cycles, both of length 3. And we got the order 3. Here we had cycle of length 2, cycle of length 3, disjoint cycles, the order was 6. So, can you guess what's going on here? What will be the order of the 4-cycle times the 2-cycle? They are disjoint. It's going to take 4 repetitions of this to make this disappear, and 2 repetitions of this to make it disappear. So 4 will be the order of this. The order is 4. if you call this, I don't know, sigma, you can check yourself, rho. Rho to the fourth is equal to the identity permutation. And in general, what do you think? How do you think we could generalize this? Well, the order of a permutation is the least common multiple of its cycle length. Now we are assuming that the permutation is simplified, that the cycles are disjoint. It's the least common multiple. And go back to those examples and you'll see why. Because it takes m times for an m cycle to disappear and n times for an n cycle to disappear. Then if they both disappear, it will be a multiple of both m and n, the least common multiple. Now we've already talked about inverses here, but just to mention it one more time, this is called a two-cycle or a transposition. A transposition, it just changes the place, transposes two of the elements of A, two numbers. What does that mean about the inverse of a transposition? Well, if it's a two-cycle, then the order is 2. So that means that, for example, the cycle 1, 2 times 1, 2, or it is equal to 1. So it means that a transposition is its own inverse. What is the inverse of 3, 4, 2, 1? Well, we said that you could write it 1, 2, 4, 3, just reverse it. That's one way. But that's the same thing as 2, 4, 3, 1. It's the same thing as 4, 3, 1, 2. Different ways to write it. But the easiest is just to change, just change the order of the permutation, change the direction of the cycle. What is the inverse of 1, 3, 2, 4, 5? Well, it's in simplest notation. So the inverse of 1, 3 is 1, 3. And the inverse of 2, 4, 5 would be 5, 4, 2. So there's the inverse. This is its own inverse, and this we have to reverse the numbers. Of course, if you want to just reverse the numbers, you could write 3, 1, 5, 4, 2. That's exactly the same thing. You just have to make sure that the numbers are going in the opposite directions. Now, this one down here, the inverse of 1, 4, 5, you want to that is not disjoint. So, this one you must multiply it together first. So this one, if we multiply it together, I write down my 1. 1 is fixed, 1 goes to 4. Go back here, 4 is fixed, 4 goes to 5. Back here, 5 goes to 2, 2 is fixed. 2 goes to 3, 3 is fixed. 3 goes to 5, and 5 goes to 1. I close. So it's just this 5 cycle, and I write the inverse by, again, I'll just reverse it. So if this is what we call gamma, then I can say gamma inverse is equal to, and I'll just 3, 2, 5, 4, 1. Many other ways to write it. And the last thing we're going to talk about is even and odd permutations. Doesn't mean these aren't numbers, so even is not going to mean a multiple of 2, of course. We're going to define it. First of all, you have to know that every permutation can be written as a product of transpositions. So let's just do some examples. If I take 1, 2, 3, 4, that is the same as, now notice I put the 1 down and I go 1, 4, and then 1, 3, and then 1, 2. This is just one way of doing it. Notice I went 1, 4, 1, 3, 1, 2. Multiply it out and see. Let's just check. Write down your 1. 1 goes to 2, 2 is fixed the rest of the way. 2 goes to 1 and 1 goes to 3, 3 is fixed. 3 goes to 1 and 1 goes to 4, 4 goes to 1. So you see? And if we have, this is written as an odd number of transpositions, we're going to call it an odd permutation. Notice I could also say 1, 2, 3, 4 is equal to 1, 4. How about 2, 5, 2, 5? What's that? That's the identity. And then I could put 1, 3, and I could put 1, 2, and maybe I'll put another 1, 2, and another 1, 2. Okay, so here's another way to write it. Notice these just cancel each other out. Those are inverses. These are inverses. So you still have 1, 4, 1, 3, 1, 2. But notice that no matter how I write this 4 cycle as a product of transpositions, it's going to have an odd number. 1, 2, 3, 4, 5, 6, 7. And that's the way it is. When you take any one of the permutations and write it as a product of transpositions, it will either always be written as an odd number or as an even number of transpositions. So that's where we get the odd and even. Let's take another one. Let's take 1, 3, 2 times 1, 2 times 3, 4, 5, 1. Okay? Now, I don't even have to simplify this. These are not disjoint, but to find out if it's even or odd, I really don't even have to simplify it. I can just say, okay, first of all, I'm going to take this one, and I'm going to write it as 1, 2, 1, 3. 1, 2 is already a transposition, so I put that in. I definitely want to have this order. And then here, I'm just going to change it to 3, 1, 3, 5, 3, 4. And I have 6 of them. So this is an even permutation. Now, we didn't simplify it, but if you're just asked, is a permutation even or odd, you just write it as a product of transpositions, and if it is an even number of transpositions, the permutation is even. If it's odd, it's odd. Okay, so just last 2 problems here. Classify the following as either even or odd and find the order of each. And why don't we find the inverse too? And inverse. So let's call this one alpha. Alright, so alpha is not disjoint. So the first thing I'm going to do, since I'm not just writing it as even or odd, I want to simplify it and write it as a product of disjoint cycles. So I'll put 1. 1 is fixed, 1 goes to 3. 3 is fixed, 3 goes to 5. 5 is fixed, 5 goes to 2. 2 goes to 4, and 4 is fixed. 4 goes to 2, and 2 goes to 1. Alright, so I have alpha is simply a 5 cycle. So I know that the order of alpha is equal to 5. I know that alpha inverse, one way to write it is just to reverse 4, 2, 5, 3, 1, so that the product of these two is the identity. And if I want to write it as a, classify it as even or odd, I think I'll just write up here, write it as a product of transpositions. I'll have 1, 4, 1, 2, 1, 5, 1, 3. And we see that there are 4 of them, so alpha is an even permutation. And gosh, this is the same kind of thing, so let's cancel that example and stop here.